Okay, so the representations are classified in terms of the dimensions. Okay, in terms of the dimension of the matrices. So you can have so for a given abstract dimension, you can have for the same abstract group, you can have one can have so several dimensional matrices. Now this is slightly confusing at the first point, but it will be clear when we see some examples. And I won't deal with discrete groups more so much in this revision of the group theory. But for the continuous groups, we'll do this. So, for example, you could have n is equal to 2, n is equal to 3, and so on. So, or the dimension of the matrix could be 2, 3, and so on. So, for the same group. Okay, now, so what we have seen so far is that there are these groups and there is this vector spaces which are called representations of this of these groups. So let's look at something more simpler. Groups in general can be classified into two parts. Two types of them. These are called discrete groups, which we have seen so far. And there is continuous groups. So what are okay? So the continuous groups, which are essentially example. So examples like which appear in physics, like rotation groups, unitary groups, orthogonal groups. These are the ones which become important for us. Actually, this is what we're going to focus on today. Okay. So discrete groups are groups like parity, charge conjugation, etc. So various things. They know whether they are discrete operators also. Okay. So there could be other. Okay, I should be not. Did me not mention this because they could have something else. Actually. Okay, rotation groups, etc. Okay. So we have seen Z2 groups like Z2, C2, Z, and these are called cyclic groups. Okay, but there is another bigger classification of these groups, which is abelian, non-abelian. Okay, so this will make it clear why matrices form a very good objects which can represent groups. Abelian means a group element say AI star AJ is equal to AJ star AI. Now non-abelian means AI star AJ is not equal to AJ star AI. Okay. So this is typical. So most of the matrices don't, if you multiply from left hand, but if you multiply uh, from right, give you completely different answers. So they don't commute. So the commutation between AI and AJ is equal to 0 here, and AI and AJ is not equal to 0. They don't commute, non-commuting. Okay. So these are commuting. Abelian groups are essentially commuting groups. Okay. Uh, so it turns out up to in the case of discrete groups, you cannot have non-abelian. The minimum order of the group, okay, should be at least 4 to start seeing non-abelian features. Okay. So in the case of discrete groups, so if you take abstract groups with order n, okay, greater than starting greater than equal to 4, you start saying okay, the abelian groups essentially should be with is less than or equal to 4, and here discrete groups n greater than or equal to 4, and this is not, there is no equal to. So discrete groups with meaning number of elements with order greater than order of the discrete group should be greater than or equal to 4. You start having something called the non-abelian groups. So you can actually check that they are non-abelian. They could be both abelian or non-abelian, but one of the first examples of non-abelian features we will start seeing there actually. Okay. So in the case of continuous groups, so one class of continuous groups which we call as the Lie groups. So U1 is abelian. UN or SUN, n greater than or equal to 2, you will start having them to be non-abelian, whereas U1 is abelian. Okay, U1 is an abelian group, and that we have seen the QED, which is explained by U1, is an abelian group. So now let's just focus a little bit more on the continuous groups, because that's where we are mostly focused on. So these also we'll focus on something called the Lie groups, which are can be which are defined as which can be continuously deformed so you can start with one and then you can always go back to another. Okay, so the Lie groups are defined. One of the examples of Lie groups are essentially unitary groups. Essentially, so unitary groups are Lie groups. We needed unitary groups because most of the symmetry operators in nature are represented by unitary groups. That's what we have seen. So we will focus on this unitary groups actually. So the unitary groups are defined with U is equal U dagger is equal to 1, where U is the group element. Now, in this case, there is something called, instead of having an abstract definition of a group, you will have something called a defining representation of the group. So that means the group itself is defined not in terms of abstract quantities, but instead is defined in terms of a representation itself. So that means it's defined in terms of a matrix itself compared to the other cases. So typically it's useful to define, in this case, it's instead of defining it in terms of some abstract quantities, you can define it directly in terms of some representation. In this case, you can directly define it in terms of matrices. Okay. Okay. The unitary groups. So the unitary group of dimension n is defined as a set of matrices which are n by n unitary and unitary. Okay. So the unitary group, so it is defined in terms of a set of matrices, but there could be other representations of this group. So you can think that, okay, so the lowest dimension which you have seen is essentially U1, which we have seen a lot the last few days. Then you can have SU2. So SU2 is defined, U2 is defined in terms of dimension of, so we'll see today in terms of dimension 2 by 2 matrices which are unitary. So U3 is defined in terms of 3 by 3 matrices which are unitary. Okay. So you are using a representation itself to define the group essentially. Okay. Un, so this is Un for a general unitary group of dimension n, is defined to be the set, the group of all n by n matrices, okay, which are unitary. Say for example, U2 would be set of all 2 times 2 matrices. U3 similarly set of all 3 by 3 matrices. U4 would be set of all 4 by 4 matrices. So what we said was a matrix would be a representation of an abstract group or something, but in this case we are using a representation itself to define a group. Okay. So now then there is another property that U1 1 by 1 matrices is abelian, whereas all these things are non-abelian. And this is an important thing. So U1, the QED theory which we have seen, is an abelian theory. So that means that, so let's take U1 theory, set of all numbers, just complex numbers. Okay, if they are just 1 by 1 matrices, it means that then set of all Zi such that Z star is equal to 1. Okay, you can think in this particular fashion. So the easiest representation would be U1 would be e power I theta. because it's continuous, theta where theta has some region essentially. Okay, some domain. So as theta takes continuous values, this is sort of goes. Now what happens is that e power I theta times e power I theta prime is equal to e power I theta prime into e power I theta is equal to e power I theta plus theta prime. So this is an abelian theory. Okay, it's an abelian group. So that's because the group elements, when you multiply with each other, they don't really bother about what order they are multiplied on essentially. So whether they are left order or right order, essentially the group elements commute with each other. The reason they commute with each other is at the top of e power I theta, there is nothing which is multiplying. It's just one unitary, which is a unit which is multiplying each other. Okay, there is no any other element which is multiplying. Like for example, if you have a matrix sitting on the top, okay, in that case e power I theta prime would be not commuting, okay, if instead of having this thing. So this is precisely what happens in the case of SU2, U2 or SU2, U2. U2, as we'll see later, as we'll see now, is a set of all 2 by 2 matrices such that they are unitary. So let's just define what U2. So let's just take a 2 by 2 complex matrix A, B, C, D, and you have the condition. This is U, A star, B star, C star, D star. This is U dagger, and you say that U star dagger is equal to 1. This straight away gives you me the conditions like mod A square plus mod B square, mod C square plus mod D square, then AC star plus BD star, A star C plus B star D is equal to this one, okay, 1 0 0 1. So in general you could have 4 complex entries. The unitary conditions so that is called 8 real numbers is equal to 4 conditions. So that leaves you 4 free parameters. But you can do more. You can ask. Okay, you can ask. It becomes more and more convenient later on actually. That you can define instead of U2, you can define something called SU2. This is called special unitary group. This in the special unitary group, you also define not just the unitarity of the two-dimensional matrices, but you also determine, put a condition on the determinant of these matrices. Determinant of U should be equivalent to +1. See, the point is that if you have this kind of a condition, if they are unitary matrices, okay, if you take, say for example, so just U dagger is equal to 1. So this means if you apply det u, okay, det becomes det u square is equal to det 1, so that is equal to 1. So this means that u could be plus or minus 1. Now the special s of u, okay, n chooses det u to be plus 1. Okay, the special unitary. So anyway, for any unitary matrix, the determinant would be plus or minus 1. Purely because u dagger is equal to 1, if you apply determinant on both sides, it gives you the det of u square is equal to det of 1. And so this implies that det u is equal to plus or minus 1. Now, if you put in the special here, so s here, that tells you that I am choosing this plus 1 here. Essentially, the determinant is even further reduced. Okay, the choice of the determinant is further reduced, and this gives me the plus 1 here. This gives me one more condition. So already we have said that there are only 4 free parameters because of the 4 conditions. Now if you have one more free out of the 4 free parameters, 4 parameters, you can reduce one more condition which are called the det condition. That gives me only 3 parameters. So essentially you end up with, so any unitary matrix, or any unitary matrix with of 2 by 2 dimensions, okay, the group of unitary matrix of 2 dimensions in general can be described only in terms of 3 parameters. That's it. There are only something called just 3 parameters. Now, so now you have these 3 parameters. Let the 3 parameters is equal to theta 1, theta 2, theta 3. Let me just say that because they are continuous variables, let me use them the angular notation, okay, just for case, okay. So SU2 has 3 parameters. Any element of SU2 can be described by these 3 parameters. Essentially, that's what it means. Okay, all the elements, all the entire group of SU2 can be described in terms of these 3 parameters. And let me say that these 3 free parameters can be written in angular variables because it's more convenient. And theta 1, theta 2, theta 3. I'll also remember one more thing. Okay, I'll also remember that any unitary matrix can be written or expressed as e power I h, where h is a Hermitian matrix. What is a Hermitian matrix? Okay, U is equal to e power I h, where h dagger is equal to h. Okay, any unitary matrix can be expressed. So in the case of S, okay, so these h, so essentially these h's, so for example, if you now represent your unitary group elements in terms of some h's, so these h operator, this is what we learn in operators actually in quantum mechanics. So I'm not going to derive, actually you can actually put it, derive it starting from the unitarity condition that this entire group can be represented in this particular fashion, e power I h actually, but I am not going to do that. I am just going to use some arguments of the physics which you already know, using the physics already know. So any unitary matrix can be expressed as e power I h, where h is an Hermitian matrix where h dagger h is equal to 1. So I want to use that. Okay, so this would mean that uh, uh, so this would be so these H's. So if I represent the unitary matrix SU2 in terms of these H's, so I would need unitary group because it's a continuous group in terms of these H's corresponding H's. Let me just put it in. These are called, they are, end up being called as, they are called as generators of the group. In the case of SU2, the generators of the group are nothing but Pauli matrices. These are nothing but Pauli matrices. Okay, so the entire SU2, the entire group SU2 can be re-expressed in terms of E. Okay, so every SU2 element essentially, every expressed can be represented as E power I theta 1 times sigma 1, maybe there is a 1 by 2 actually, 2 times sigma 2 times sigma 3 theta 3 times sigma 3 by 2, where sigma 1 is equal to the Pauli matrix X, okay, sigma X, sigma 2 is equal to the Pauli matrix Y, sigma 3 is okay 1 0 0. So the Pauli matrices. So every element of SU2 is given in terms of this e power I, where theta can take values. Okay, some because it's an angular values, so you can take some. Okay, let's just take theta some values, and depending upon the value of theta, you'll have all the elements essentially. Theta is some random complex number essentially. So let's just put it back into this. Okay, so what you have, just let me just say that this is true. So what you have SU2, okay, so any element, let's take element say, and just explore this matrix, this terminology a little bit more. E power, so this is given element of SU2, so let's just study SU2 essentially. So E power I theta 1 dot sigma 1 plus, or maybe there is a by 2 here, theta 2 times sigma 2 plus theta 3 times sigma 3. So if I expand this essentially, this, if I just take theta to be small as close to 0, so that means this is 1 plus theta 1 plus sigma 1 plus theta 2 plus sigma 2 plus theta 3 times sigma 3. This is roughly 1, which is means identity matrix, plus theta 1 times sigma 1, I know what it is, that is nothing but theta 1 minus I theta 2 theta 3 theta 1 plus I theta 2 minus theta 3, and so on, so on, so on. Because it's an exponential series, so you can have an expansion in this particular manner. For small theta essentially. So for infinitesimal parameters, so these thetas, let me call them as small theta, let me call them as delta theta, say for example. Let me call them as delta 1, delta 2, delta 3, just to distinguish that these are smaller parameters, delta 1, delta 2, delta 3. So these are this small parameters sitting here. Now you see that when the delta goes to 0, you get back to unity. So it is a small modification to unity. And this transformation, what does it? Let's just see what is the so in this defining representation, what is the operations these do? What is the operations this SU2 group do? Say for example, let's just take a vector and apply. If I apply an SU2 transformation, say for example, let's take an element, say consider a vector. So let me call this as Z1, Z2. So if I take a vector Z1, Z2 and apply SU2. So what I want is essentially what happens with if I apply SU2. So SU2, what does it do? So SU2 is, so let me call as Z1 prime, Z2 prime is equal to e power I theta bar dot sigma bar acting on Z1, Z2. This I know is an expansion to unity. So this will be at a very small data. So delta 1, delta 3, delta 1 minus I delta 2, delta 1 plus I delta 2 minus delta 3 acting on Z1 and Z2. So the unit transformation doesn't do anything, it just keeps the this one. Okay, let me expand this one again. So let's do the summation. This is equal to Z1 plus Z2, it won't modify anything, plus, okay, the first term would be delta 3, the first transformation would be delta 3, delta 1 plus Z2, so the other combination, okay, the other one would be, okay, these kind of things. So delta 1, delta 1 times delta 3 times Z2, delta 1 minus I delta 2, Z2, delta 3. So this is the transformation it does. So what it does is, I did something mistake, this is that one. So what it does, it mixes Z1 and Z2. So it's a transformation which it's like a spin, it mixes Z1 and Z2. Okay. So in particular, if delta 3 is equal to 0, delta 1 and delta 2, what do they do? Delta 1 and delta 2 interchange Z1 to Z2. So they flip, wherever there is a Z2, they bring in Z1, and wherever there is a Z1, they bring Z2. That's the transformation under which these act. Okay. And on the other hand, if we have a Z3, it is just essentially a modification. Okay, when delta 1 and delta 2 are 0, okay, Z3 just adds a minus sign to them. Essentially, it's sort of a unitary transformation, but with sort of a minus sign on the other thing for the second component. For the second component. So the first two components sort of interchange, meaning so they bring a small fraction of Z2 into the first element, essentially Z1 and Z2 as Z, because delta 1 is a very small thing, but you can keep increasing this thing. Okay, you can keep using this infinitesimal transform. So you can now start with an infinitesimal transformations and then apply it again and again and again and again. So that means you start applying this infinitesimal transformations once you meaning power n. So it just becomes an exponential application of infinitesimal transformations, and you get back this full thing e power I theta on the reverse also, and from the converse also you can get back the same thing. But anyway, so let's just do what does SU2 do. SU2 does is that it interchanges Z1 and Z2 by a small amount. That's important that we remember it. For an arbitrary amount, for a small infinitesimal, it just is this given by the parameter of the theory essentially. Okay, there is an interchange factor where Z1 and Z2 are interchanged. This will be useful for us for in the later purposes essentially. Okay, to understand why SU2 becomes an important theory. And the other part of the SU2 separates Z1 and Z2 by a minus sign. So it can be used as a labeling operator, just like in spin. So does it remember you the spin group? Essentially, it's exactly like spin, and it is the spin thing, which is essentially that the delta the tau 3 or the sigma 3 can be used as a labeling operator, whereas tau 1 plus tau 2 or sigma 1 plus sigma 2 can be used as a raising and lowering operators for this thing. So you can actually build representations from the spin algebra. So you can just use the spin algebra or the angular momentum algebra and build all the representations which you want. Now, uh, now the other important thing about SU2 is that because these are matrices sitting on the top of this thing in the exponentials, say for example, you are having two exponentials. So if you have two elements of the SU2 group, they don't commute with each other. So it's a non-commuting, non-abelian group. Okay, that we can see now itself. So if you have SU2, an element of SU2 which is defined by so SU2 element, so e power I theta dot sigma 2, and another SU2 element which is defined by e power I theta dot sigma bar sigma by 2. Now let me call the second one as theta prime, just to distinguish between okay, this one as a one element and this is as another element. This actually is not equal to e power I theta dot plus theta prime sigma by 2. This is not equal to, so this is not a commutative relation. So what happens is this, you have to use something called the Baker-Hofstra formula. So this e power I theta times sigma, it's a matrix A, times e power I theta primes dot sigma. So let me just forget about the factor 2's here for a while, would be equivalent to, so e power I theta, so it would be equivalent to a bunch of commutators essentially, okay, plus theta prime sigma by 2 plus commutator 1 by 2 Okay, let me just write it down rather than writing in terms of the sigmas. So this will be, so if you have a matrix e power a times e power b equal to e power a plus b plus 1 by 2 a b and so on. So there's a series. So where the commutator enters essentially. So this is, as long as these matrices don't commute, these are a, b are some matrices. Okay. So if you have matrices in the exponential, if you write e power a times e power b, they don't actually commute. So this SU2 group is actually a non-abelian group. Now one can generalize this. So in general, okay. So in general, all this is a true property of all the SUN groups are non-abelian for n greater than or equal to 2. Okay, and the number of free parameters is n square minus 1. This you can use it as a homework problem. So the number of free parameters. So the number of free parameters is equal to the number of generators. So the number of generators is also equal to n square minus 1. This is an important point actually. Okay. So the number of free parameters is equal to n minus 1 and number of generators is equal. So the defining representation, the defining representations, now let's coming to the representation properties. So these are the number of uh, number of generators and number of free parameters. Now we'll just look at one so the defining properties of this non-abelian gauge series, or like let's start, will be represented by what is this commutators of these generators, because this is what sits in this matrix. Okay, in the multiplication of the exponentials in the group multiplication law. So in the group multiplication law, you have here a bunch of taus, here another bunch of taus, and this is the commutator between the taus or between the sigmas. So the group multiplication law is crucially determined by the commutator of the generators. Okay, so the commutator of the generator for the SU2 has sigma I, sigma j is equal to I epsilon I j k sigma k. So this is the commutator. This essentially determines your group multiplication law. So if there is any representation whose as long as any representations satisfies this group commutation law, that is essentially okay, any representation which also satisfies the group multiplication law, that is also gives you it forms a representation other than the defining representation. Okay, let me make it better. So the defining representation is typically called something called the fundamental representations. So let's look at representations. So the defining representation is also called the fundamental representation. So this is a representation. So this is Z1 and Z2. So for example, in which case the sigma matrices are just two-dimensional. And there could be other representations. You could have something called adjoint representations. Okay, they are called adjoint representations, which are the representations of the group generators. Okay, they are three-dimensional. So they are three-dimensional matrices which follow the group. What do you call algebra? This is actually called the commutator relationship or the group algebra. It's also called the group algebra. They are representations of the group algebra. So they are dimension 3 matrices, which are this we see in the spin 1 represent. It's like the spin 1 representation under spin matrices, right? Essentially, that you have when so gen j is equal to half, you have the fundamental representation in words of the quantum mechanics, and j is equal to 1, you have three-dimensional matrices in the spin group, essentially in the spin matrices. So that forms something called the adjoint representation. And it's all dimension 3 is 3 by 3 matrices which satisfy the representation of the group computation algebra. Okay, group algebra. We have to distinguish. There is actually technically a distinction between the group algebra and also the group multiplication law, but as of now, let's leave it as that, essentially. Okay, so uh, I sort of tried to revise today actually all the basic properties of the uh, group theory. Okay, um, elements of the group theory, which we would require actually in understanding in the next few lectures, especially for the understanding of the strong interactions. Okay, uh, what I tried to summarize is only the final results of all the group theory. I have not derived any of these final things. I just said there are these the group is represented by unitary groups are represented by an exponential times some Hermitian matrices, and these Hermitian matrices are called generators. Okay, these Hermitian matrices are called generators. For the SU2 case, these generators are nothing but the sigma matrices. Okay, and these sigma matrices have a commutation role between them. They are not commuting, so they are non-abelian groups. Okay, so if you want to build a representation of the SU2, what it matters is that these points are important. That so there are a couple of representations which we have looked at. One is called the fundamental representation, which is nothing where the sigma matrices are just two-dimensional, but you can also have three-dimensional sigma matrices, as in spin 1 representation. Okay, in quantum mechanics, like for example. Okay, the spin 1. So similarly, you can have three-dimensional representations here also for the SU2. That representation is called an adjoint representation. Now, in the next lecture, we'll look at SU3 and maybe a little bit of O3. Okay, some elements of orthogonal groups and also for unitary groups actually. And then we'll move to QCD. I know. Okay. So the takeaway points are just the number of free parameters for a unitary matrix and number of what are these Hermitian generators, meaning the Hermitian matrices sitting in exponential point. That unitary matrices can be written in terms of this exponential power, the Hermitian operators. So these Hermitian matrices are nothing but the generators of the group. Okay, this is the basic takeaway point from this lecture. Once you know this, so what we will say is that these SU2 are symmetric transformations now. Okay, instead of using the unitary transformations, we can use this SU2 unitary transformation. So this will become slightly more complicated symmetric transformations compared to the case of unitary transformations which we have seen here so far. And so they are also non-abelian, which will include some additional complications associated with this in field theory. We will see that also in the next few lectures. Okay, let me stop here.